There is a photograph that changed everything. Not because of what it shows, but because of what it proves. In April 2019, scientists released an image that had taken 8 radio telescopes scattered across 4 continents, 200 researchers, and 2 years of painstaking analysis to create. What you see in that image is a ring of superheated gas, swirling at nearly the speed of light, surrounding a shadow darker than anything in the universe. You are looking at the event horizon of a supermassive black hole. You are looking at the point of no return, 55 million light-years away, in a galaxy called Messier 87. And you are looking at proof that the most extreme predictions of Einstein's general relativity, made over a century ago, were not mathematical abstractions. They were reality. But this image is just one of 5 discoveries that have fundamentally transformed our understanding of the cosmos in recent decades. 5 moments when humanity's instruments pierced through the darkness and found something that rewrote the textbooks. Something that made us smaller and larger at the same time. Smaller, because we realized how little we truly knew. Larger, because we proved we could know anything at all. You live in an extraordinary time. The past 30 years have witnessed more revolutionary discoveries about the universe than the previous 3 centuries combined. We have detected ripples in the fabric of spacetime itself. We have found thousands of worlds orbiting distant stars. We have watched galaxies accelerate away from us, pushed by a force that makes up most of the universe yet remains completely invisible. We have discovered oceans of liquid water hidden beneath the icy shells of moons we once dismissed as frozen, dead rocks. These are not incremental advances. These are earthquakes. And they all share something in common. Each discovery began with a question that seemed impossible to answer. Each required instruments and techniques that did not exist when the question was first asked. And each revealed a universe far stranger, far more dynamic, and far more full of possibility than we had dared to imagine. Consider for a moment where we stood just a generation ago. In 1990, we had never confirmed a single planet outside our solar system. The existence of exoplanets was theoretical, debated, uncertain. We did not know if our solar system was typical or unique. We did not know if the conditions that allowed life to emerge here existed anywhere else in the cosmos. We were, in a very real sense, alone in our ignorance. Today, we have confirmed more than 5,000 exoplanets. 5,000 worlds, each with its own story, its own history, its own potential. Some are gas giants larger than Jupiter, orbiting so close to their stars that their years last mere hours. Others are rocky, Earth-sized, nestled in the habitable zones where liquid water could pool on their surfaces. The Kepler Space Telescope, launched in 2009, found most of them by staring at a single patch of sky for 4 years, watching for the tiny dimming of starlight when a planet crosses in front of its host star. That dimming is so slight that if you were watching a lighthouse from a mile away, it would be like detecting a moth passing in front of the beam. Yet Kepler saw it, again and again, around star after star. The James Webb Space Telescope has taken this further. Launched in December 2021, Webb can do something Kepler never could. It can analyze the light passing through an exoplanet's atmosphere, breaking it into its component wavelengths, reading the chemical fingerprints of molecules present in those alien skies. In 2023, Webb detected carbon dioxide in the atmosphere of a planet called WASP-39b, a hot gas giant 800 light-years away. This was the first unambiguous detection of this molecule on a world beyond our solar system. But carbon dioxide was just the beginning. Webb has since found water vapor, methane, sulfur dioxide. We are reading the compositions of atmospheres we will never visit, around stars we will never reach, and learning that the chemistry of distant worlds is far more complex and varied than we ever expected. But here is what makes this era truly remarkable. The discovery of exoplanets is not an isolated achievement. It exists within a web of interconnected breakthroughs, each one illuminating the others, each one raising new questions that demand new answers. In September 2015, two enormous L-shaped detectors, one in Louisiana and one in Washington state, simultaneously registered a signal that had traveled 1.3 billion years to reach us. That signal was a gravitational wave, a ripple in spacetime itself, generated when two black holes, each about 30 times the mass of our Sun, spiraled together and merged. The collision released more energy in a fraction of a second than all the stars in the observable universe combined. Yet by the time that wave reached Earth, it had stretched and compressed our planet by less than 1,000th the width of a proton. The LIGO detectors found it anyway. They found it because human ingenuity had created the most sensitive measuring instruments ever built. Think about what this means. For all of human history, we observed the universe through light. Visible light, radio waves, X-rays, infrared, gamma rays, different forms of electromagnetic radiation. This was our only window. Gravitational wave astronomy opened a second window. We can now perceive the universe in an entirely new way. We can hear the cosmos as well as see it. And what we have heard has already surprised us. The black holes LIGO detected were not where we expected them to be. Their masses did not match our predictions. Some were far heavier than the black holes we thought could form from dying stars. Where did they come from? How did they grow so large? These questions remain open, and each new detection adds complexity to the puzzle. By now, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events. Merging black holes. Merging neutron stars. Perhaps even collisions between black holes and neutron stars. Each event is a message from the violent heart of the universe, encoded in the subtle stretching of space and time. Each event carries information about objects so dense, so extreme, that light cannot escape from them. Before LIGO, we could only infer the existence of black holes from their effects on nearby matter. Now we can feel them collide. And this brings us back to that photograph. The image of the black hole in Messier 87. Because gravitational waves and direct imaging are two different ways of studying the same fundamental mystery. Black holes are predictions of general relativity. Einstein's equations said they should exist, but Einstein himself was uncertain. The mathematics described something so extreme, so counterintuitive, that it seemed more like a failure of the theory than a feature of reality. How could there be regions of space from which nothing, not even light, could escape? How could matter compress to infinite density? Surely nature would find a way to prevent such absurdity. Nature did not. The Event Horizon Telescope proved it. By linking radio dishes on 6 continents into a single virtual telescope the size of Earth, astronomers created an instrument with enough resolution to see details the size of an orange on the surface of the Moon. What they saw in Messier 87 was the shadow of the event horizon, the boundary beyond which escape becomes impossible. The bright ring surrounding that shadow is material spiraling inward, heated to billions of degrees, emitting radiation as it falls toward oblivion. You are living through the confirmation of phenomena that seemed like science fiction just decades ago. Black holes exist. Gravitational waves ripple through the cosmos. Thousands of worlds orbit other stars. And there is more. Because while we were looking outward, we also discovered something about the universe as a whole that no one expected. In 1998, two independent teams of astronomers were studying a particular type of exploding star called a Type Ia supernova. These explosions are useful because they all release approximately the same amount of energy. They are cosmic standard candles. By measuring how bright a Type Ia supernova appears, you can calculate how far away it is. By measuring how much its light has been redshifted, stretched toward longer wavelengths by the expansion of the universe, you can calculate how fast it is receding. The teams expected to find that the expansion of the universe was slowing down. After all, gravity pulls matter together. The mutual attraction of all the galaxies in the universe should be acting like a brake, gradually decelerating the cosmic expansion that began with the Big Bang. What they found instead was the opposite. The expansion is accelerating. Distant galaxies are flying away from us faster and faster, as if something is pushing them, something that grows stronger as space itself expands. We call this something dark energy. We call it that because we do not know what it is. Dark energy makes up approximately 68% of the total energy content of the universe. It is the dominant component of reality. And we cannot see it, touch it, or directly detect it. We know it exists only because of what it does. It pushes. It stretches space. It accelerates the expansion that will eventually isolate every galaxy in its own private bubble of emptiness, forever beyond the reach of its neighbors. This discovery earned the 2011 Nobel Prize in Physics. It remains one of the deepest mysteries in science. The cosmological constant, the simplest explanation for dark energy, requires a value so precisely tuned that it seems almost absurd. If it were slightly larger, the universe would have expanded too fast for galaxies to form. If it were slightly smaller, the universe would have collapsed back on itself long ago. We exist in a narrow window, a cosmic Goldilocks zone of dark energy, and we do not know why. But perhaps the discovery that strikes closest to home, the one that most directly touches the question of whether we are alone, comes not from distant galaxies but from our own solar system. In the outer reaches, far from the warmth of the sun, moons that were once dismissed as frozen relics have revealed secrets that change everything. Enceladus is a tiny moon of Saturn, barely 300 miles across. It is coated in ice so white and reflective that it is one of the brightest objects in the solar system. For decades, we thought it was geologically dead. Then the Cassini spacecraft arrived. Cassini orbited Saturn from 2004 to 2017, and during that time, it flew through something impossible. Geysers. Plumes of water vapor and ice particles erupting from fractures near Enceladus's south pole, shooting hundreds of miles into space. Cassini flew through those plumes. It tasted them. Its instruments detected water, salts, silica particles, and organic molecules. Beneath that icy shell lies a global ocean of liquid water, kept warm by tidal heating as Saturn's gravity flexes the Moon's interior. That ocean has a rocky seafloor. It has hydrothermal vents. It has chemistry. Europa, a moon of Jupiter, tells a similar story. Its surface is a chaos of cracked ice, jumbled blocks, and smooth plains that suggest the shell is floating on something liquid beneath. The Galileo spacecraft, which orbited Jupiter in the 1990s, detected the magnetic signature of a salty subsurface ocean. Europa's ocean may contain twice as much water as all of Earth's oceans combined. And where there is liquid water, where there is energy, where there are the right chemical ingredients, there is the possibility of life. These discoveries have transformed astrobiology from speculation to science. We no longer wonder if habitable environments exist beyond Earth. We know they do. The question now is whether those environments actually harbor life. And answering the question will require missions we are only beginning to plan. Europa Clipper, launching soon, will study Jupiter's moon in unprecedented detail. Future missions may land on these icy shells, melt through them, and send submarines into the dark waters below. You are witnessing the opening chapter of a story that could end with the greatest discovery in human history. Or it could end with silence, with the confirmation that Earth is unique, that life is rare, that we are alone in ways we cannot yet comprehend. Either answer would be profound. Either answer would change us. These 5 discoveries share a common thread. They all emerged from decades of patient work, from instruments built to detect what had never been detected, from collaborations spanning nations and disciplines. They all challenged assumptions. They all revealed a universe more dynamic, more extreme, more full of possibility than the one we thought we knew. But there is something deeper here, something that goes beyond the individual breakthroughs. These discoveries are connected. The techniques that find exoplanets inform the search for life on icy moons. The gravitational waves that reveal black hole mergers also help us understand the expansion of the universe. The dark energy that accelerates cosmic expansion shapes the very structure within which galaxies and stars and planets form. We are not learning isolated facts. We are assembling a picture. And that picture, though far from complete, is beginning to show us our place in a cosmos far grander than we ever imagined. What does it mean to live in a universe where black holes collide, where thousands of worlds orbit distant suns, where oceans hide beneath alien ice, where dark energy pushes reality apart? What does it mean to be the species that discovered these things, the species that built the instruments, asked the questions, and refused to accept not knowing as an answer? These are the questions we will explore together. Not as distant observers, but as participants in one of the greatest intellectual adventures in human history. The story of how we found out what we found out. The story of what it means. There is a tendency, when confronted with discoveries of this magnitude, to feel small. To look up at the night sky and sense your own insignificance against the backdrop of billions of galaxies, each containing billions of stars. But consider this. The universe is vast beyond comprehension, ancient beyond imagination, and yet it produced you. It produced a species capable of asking these questions, capable of building these instruments, capable of reaching across the light years with nothing but ingenuity and determination. The atoms in your body were forged in the cores of stars that died before our sun was born. The calcium in your bones, the iron in your blood, the oxygen you breathe, All of it was synthesized in stellar furnaces and scattered across space by supernova explosions. You are made of star stuff, as Carl Sagan famously said. But you are also made of curiosity. And that curiosity has carried you further than any physical journey could. In the chapters ahead, we will dive deeper into each of these discoveries. We will walk the surfaces of worlds we have never visited. We will stand beside the scientists who made these breakthroughs, feel their doubt and their exhilaration. We will learn the techniques they used, the obstacles they overcame, the moments when everything changed. But more than that, we will confront the questions that remain unanswered. Because for every mystery we have solved, 10 more have emerged. The universe does not yield its secrets easily. It rewards persistence and punishes assumption. And it always has more to teach. So take a breath. Settle in. The journey is just beginning. And where it leads may be stranger than anything you have ever imagined. So where do we go from here? You have glimpsed the peaks. The black hole shadow burning in the darkness of Messier 87. The gravitational waves rippling through spacetime from collisions a billion years past. The thousands of worlds circling distant suns. The hidden oceans beneath shells of ice. The dark energy pushing the cosmos apart. These are the landmarks of our journey. But to truly understand them, to feel their weight and their wonder, we need to build something first. A foundation. A way of seeing that will transform these discoveries from headlines into revelations. By the end of this journey, you will understand how we photograph objects that emit no light. You will know why the collision of two black holes can be detected by measuring a change smaller than the width of an atom. You will grasp why finding a single molecule in an alien atmosphere can tell us whether a planet might harbor life. You will comprehend why the universe's acceleration forces us to accept that most of reality is made of something we cannot see or touch. And you will feel, in a way that goes beyond intellectual understanding, why the discovery of liquid water beneath frozen moons has transformed our sense of what is possible. But these are not simple stories. They are layered, interconnected, built on centuries of accumulated knowledge and decades of technological innovation. To appreciate them fully, you need to understand how we see the universe at all. How we extract information from light that has traveled millions or billions of years to reach us. How we measure distances so vast that they strain the limits of language. How we distinguish between what we know, what we suspect, and what remains utterly mysterious. This is not a detour. This is the path. Because the wonder of these discoveries lies not just in what was found, but in how it was found. In the ingenuity, the persistence, the sheer audacity of the methods that made them possible. Let us begin with light. Everything we know about the universe beyond our own planet, we learned from light. Not just visible light, the narrow slice of the electromagnetic spectrum that your eyes can detect, but the full range of radiation that permeates the cosmos. Radio waves with wavelengths longer than football fields. Microwaves that carry the afterglow of the Big Bang. Infrared radiation that reveals the warmth of objects too cool to glow visibly. Ultraviolet light that traces the hottest, youngest stars. X-rays that illuminate matter spiraling into black holes. Gamma rays that announce the most violent explosions in the universe. Each of these forms of light tells a different story. Each requires different instruments to detect. And each has revealed aspects of the cosmos that would be invisible to any other method. The history of astronomy is, in many ways, a history of expanding our vision. Of building new eyes to see what was always there but hidden from us. Consider what happens when light passes through gas. Some wavelengths are absorbed. Others pass through unchanged. The pattern of absorption depends on which atoms and molecules are present. Hydrogen absorbs at specific wavelengths. Oxygen at others. Carbon dioxide, methane, water vapor, each leaves its own unique fingerprint in the spectrum of light. This is spectroscopy, and it is perhaps the most powerful tool in astronomy. When we point a telescope at a star, we do not just see a point of light. We see a story written in wavelengths. The dark lines crossing that spectrum, called absorption lines, tell us what elements are present in the star's outer atmosphere. The brightness at different wavelengths tells us the temperature. The width of the lines tells us about pressure, density, and motion. A star's spectrum is a biography, and astronomers have learned to read it with extraordinary precision. But spectroscopy does more than analyze stars. It reveals the composition of galaxies millions of light-years away. It detects the chemical makeup of interstellar clouds where new stars are being born. And now, with instruments like those aboard the James Webb Space Telescope, it reads the atmospheres of planets orbiting other stars. When we say that Webb detected carbon dioxide on WASP 39b, what we mean is that Webb captured the light of the host star as it passed through the planet's atmosphere, spread that light into its component wavelengths, and found the telltale absorption signature of carbon dioxide molecules. We never touched that atmosphere. We never visited that world. We read its chemistry from 800 light-years away, using nothing but light and mathematics. This is how we will search for signs of life on distant worlds. Not by sending spacecraft, at least not yet, but by reading atmospheric spectra. Certain combinations of gases are difficult to explain without biology. Oxygen and methane together, for instance, should not coexist for long. Methane is destroyed by oxygen. Oxygen is consumed by methane. If both are present in an atmosphere, something must be replenishing them. On Earth, that something is life. Photosynthesis produces oxygen. Methanogenic bacteria produce methane. The simultaneous presence of both is a biosignature, a chemical hint that something is alive. We have not found such a signature on another world. Not yet. But we now have the tools to look. The James Webb Space Telescope, with its 6.5-meter gold-plated mirror and its suite of infrared instruments, can analyze the atmospheres of rocky planets in the habitable zones of nearby stars. If life exists on one of those worlds, and if that life has altered the atmosphere in detectable ways, we may find it within our lifetimes. This is not speculation. This is the explicit scientific goal of missions currently operating. But to appreciate how remarkable this is, you need to understand the challenge. An exoplanet does not emit much light of its own. It reflects a tiny fraction of its star's light, and that fraction is overwhelmed by the star's glare. Imagine trying to see a firefly hovering next to a searchlight, from 1,000 miles away. That is roughly the contrast between a star and the planets orbiting it. To detect the firefly, you need to block the searchlight. To analyze an exoplanet's atmosphere, you need to separate its faint signal from the overwhelming brilliance of its star. There are several ways to do this. The transit method, used by Kepler and now by the transiting Exoplanet survey satellite, watches for the dimming of a star when a planet passes in front of it. That dimming is slight, often less than 1%, sometimes as little as 1/100%. But it is measurable. And during a transit, some of the star's light passes through the planet's atmosphere, picking up those spectroscopic fingerprints we discussed. This is how we read alien atmospheres. Not by looking at the planet directly, but by analyzing the star's light as the planet blocks and filters it. Another method is direct imaging. This requires blocking the star's light with a device called a coronagraph, creating an artificial eclipse inside the telescope. With the star's glare suppressed, the faint reflected light of orbiting planets can sometimes be seen. Direct imaging works best for large, young, hot planets far from their stars. Earth-sized planets' inhabitable zones remain beyond its reach, at least for now. Future space telescopes, currently in the planning stages, will carry coronagraphs sophisticated enough to image Earth-like worlds around nearby stars. The radial velocity method detects planets by the wobble they induce in their host stars. A planet does not simply orbit a star. Both the planet and the star orbit their common center of mass. For a system like Jupiter and the Sun, that center of mass lies just outside the Sun's surface. As Jupiter orbits, it tugs the Sun in a small circle. From a distant vantage point, you would see the Sun shifting slightly toward you and then away from you, over and over, with a period of 12 years. That motion shifts the Sun's spectrum. When the Sun moves toward you, its light is blue shifted. When it moves away, it is red shifted. By measuring these spectral shifts, you can infer the presence of a planet you have never directly seen. This is the power of modern astronomy. We do not need to visit distant worlds to learn about them. We do not need to touch them. We analyze photons that have traveled unimaginable distances, decode the information they carry, and reconstruct the properties of objects we will never reach. But light is not our only messenger. We mentioned gravitational waves in the previous chapter, and they deserve deeper explanation here. Because gravitational wave astronomy is not just a new tool. It is an entirely new sense. Imagine you have spent your entire life deaf. You have learned about the world through sight, through touch, through smell and taste. You have developed sophisticated instruments to detect vibrations in the air, to translate them into visual patterns you can study. You know, intellectually, that sound exists. But you have never heard a symphony. You have never heard a voice. You have never heard the crash of waves on a shore. Then one day, someone gives you the ability to hear. Suddenly, the world is different. Not because anything has changed, but because you can perceive what was always there. Events you could only see now have a sonic dimension. Explosions roar. Wind whispers. The universe is richer, deeper, more layered than you ever imagined. This is what happened on September 14, 2015, when LIGO detected its first gravitational wave. We gained a new sense. We heard the universe for the first time. Gravitational waves are ripples in spacetime itself. They are predicted by Einstein's general theory of relativity, which describes gravity not as a force but as a curvature of space and time caused by mass and energy. When massive objects accelerate, they send ripples outward through that curved spacetime, just as a boat sends ripples across water. Those ripples carry energy and information. They stretch and compress space as they pass. The problem is that gravitational waves are incredibly weak by the time they reach us. The waves LIGO detected were generated by two black holes, each about 30 times the mass of our Sun, spiraling together and merging. That collision released more energy than all the stars in the observable universe combined. Yet by the time those waves reached Earth, after traveling 1.3 billion years, they had spread out so much that they stretched and compressed space by less than 1,000th the diameter of a proton. A proton is already unimaginably small. 1,000th of that is beyond ordinary comprehension. How do you measure something so tiny? LIGO does it with lasers and mirrors. The detector consists of two perpendicular arms, each 4 kilometers long. A laser beam is split and sent down both arms, where it bounces off mirrors and returns. When the two beams recombine, they create an interference pattern that depends on the exact difference in their travel times. If a gravitational wave passes through, it stretches one arm while compressing the other. This changes the interference pattern. The change is minuscule, but LIGO's sensitivity is staggering. It can detect changes in arm length smaller than 1/10,000th the diameter of a proton. To achieve this, the mirrors must be among the most precisely positioned objects humans have ever created. They are suspended by glass fibers to isolate them from vibration. The laser light circulates hundreds of times between the mirrors to amplify the signal. Sophisticated algorithms filter out noise from earthquakes, traffic, even the quantum fluctuations of the laser itself. LIGO is not just a detector. It is a triumph of engineering at the absolute limits of what is physically possible. And it works. Since that first detection, LIGO and its partner observatory Virgo in Italy have detected dozens of gravitational wave events. Merging black holes. Merging neutron stars. Some of these events have been simultaneously observed with conventional telescopes, combining gravitational and electromagnetic information. This is multi-messenger astronomy, the use of completely different types of signals to study the same cosmic event. It is like watching a thunderstorm and hearing it at the same time. The neutron star merger detected in August 2017 was particularly revolutionary. Gravitational waves arrived first, detected by both LIGO and Virgo. Within seconds, a burst of gamma rays was detected by space-based observatories. Then, over the following days and weeks, the afterglow was observed across the electromagnetic spectrum, from radio waves to X-rays. For the first time, we witnessed the same event with multiple senses. And what we learned was profound. Neutron star collisions forge heavy elements. Gold, platinum, uranium, the atoms that require extraordinary conditions to form, are synthesized in the fiery aftermath of these mergers. The merger LIGO detected produced an amount of gold estimated at several Earth masses. We are not just seeing the universe. We are watching it create the elements that make up everything around us, including ourselves. There is one more foundation stone we need to lay before we dive deeper into our 5 discoveries. We need to understand how we measure cosmic distances. This is not a trivial question. You cannot stretch a tape measure to a galaxy 100 million light-years away. You cannot bounce radar off a black hole. Distance in astronomy is inferred, not directly measured. And the methods we use form a ladder, each rung calibrated by the one below it. The first rung is parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. By measuring this shift, you can calculate the star's distance using simple trigonometry. Parallax works well for stars within a few thousand light-years, but beyond that, the shifts become too small to measure accurately. The next rung uses standard candles, objects whose intrinsic brightness is known. If you know how bright something truly is, and you measure how bright it appears, you can calculate its distance. The dimmer it appears, the farther away it is. Cepheid variable stars are one type of standard candle. Their brightness pulsates with a period that correlates with their intrinsic luminosity. By measuring the period, you determine the luminosity. By measuring the apparent brightness, you determine the distance. Type Ia supernovae are another standard candle, and they are visible across much greater distances. These are the explosions we mentioned earlier, the ones used to discover the accelerating expansion of the universe. They occur when a white dwarf star accumulates enough matter to exceed a critical mass and detonates. Because the critical mass is always the same, the explosion is always approximately the same brightness. Type Ia supernovae can be seen billions of light-years away, allowing us to measure distances across most of the observable universe. But here is the crucial point. Each rung of this ladder depends on the rungs below it. We calibrate Cepheid distances using parallax. We calibrate supernova distances using Cepheids. Any error in the lower rungs propagates upward. And there are errors. The current tension between different measurements of the universe's expansion rate, known as the Hubble tension, may reflect exactly this kind of systematic uncertainty. Or it may indicate new physics we do not yet understand. This is the nature of science. We build our knowledge carefully, testing each step, aware that what seems solid today may require revision tomorrow. The discoveries we are about to explore rest on this foundation. They emerge from spectroscopy and gravitational wave detection and distance measurements and 1,000 other techniques refined over centuries. You now have the tools to go deeper. You understand how we read the light of distant worlds. You understand how we listen to the collisions of black holes. You understand how we measure the vast distances that separate us from the farthest reaches of the cosmos. The foundation is laid. The journey continues. And the first stop is the discovery that rewrote our understanding of what lies beyond our solar system. The discovery of other worlds. The story of how we found other worlds begins with a failure. A spectacular, humiliating, very public failure. In 1963, astronomer Peter van de Kamp announced that he had discovered a planet orbiting Barnard's star, a dim red dwarf just 6 light-years from Earth. He had spent decades photographing that star, measuring its position with painstaking precision, looking for the tiny wobble that would betray the gravitational tug of an unseen companion. And he found it. Or so he believed. The astronomical community celebrated. Textbooks were updated. For nearly 20 years, the planet orbiting Barnard's star was considered a confirmed discovery. Then it fell apart. Other astronomers, using better instruments, could not reproduce van de Kamp's results. Investigators discovered that the wobble he had measured was not caused by a planet at all. It was caused by adjustments to the telescope's lens. Every time the observatory's equipment was serviced, tiny changes in the optical system had mimicked a planetary signal. Van de Kamp had not discovered a world. He had discovered an instrumental artifact. The retraction was devastating. A career defined by this search ended in embarrassment. The first exoplanet was not the first exoplanet after all. This matters because science is not a march of unbroken triumphs. It is a stumbling, self-correcting process, littered with false starts and blind alleys. The path to our current understanding of exoplanets is paved with disappointments, with discoveries that were not discoveries, with years of work that led nowhere. And the people who walked that path were not abstract intellects. They were human beings who risked their reputations, invested their lives, and sometimes watched everything crumble. But they kept going. Because the question was too important to abandon. Are there other worlds out there? Are we alone? For most of human history, this question belonged to philosophy, not science. The ancient Greeks debated whether other worlds existed. Giordano Bruno was burned at the stake in 1600, in part for insisting that stars were distant suns with their own planets. But until the late 20th century, we had no way to know. Planets are small. Stars are bright. The distances are immense. Finding a planet around another star seemed almost impossible. The breakthrough came not from looking, but from listening. In 1992, astronomers Alexander Wolszczyn and Dale Frail announced the detection of two planets orbiting a pulsar, a rapidly spinning neutron star that emits beams of radiation like a cosmic lighthouse. Pulsars are nature's most precise clocks. Their radio pulses arrive with such regularity that even tiny variations stand out. Wolszczyn and Frail noticed that the pulses from a pulsar called PSRB 1257+12 were arriving slightly early sometimes, slightly late other times. The pattern was periodic. Something was tugging on the pulsar, shifting it back and forth. That something was planets. This was extraordinary. But it was also strange. Pulsars are the remnants of supernova explosions, cataclysms that should have destroyed any planets in the system. How could worlds exist around such a violent object? Where did they come from? The discovery raised as many questions as it answered. And because pulsars are so different from ordinary stars, it did not tell us what we really wanted to know. Were there planets around stars like our Sun? 3 years later, we found out. Michel Mayor and Didier Queloz were using a spectrograph at the Haute-Provence Observatory in southern France, measuring the subtle spectral shifts that reveal a star's motion toward and away from us. They were not expecting to find a planet quickly. The search was supposed to take years, maybe decades. The planets they hoped to detect would cause wobbles unfolding over months or years, similar to Jupiter's 12-year orbit. They were patient. They were methodical. They were completely unprepared for what they found. The star was 51 Pegasi, a Sun-like star about 50 light-years away. The wobble was clear. Unmistakable. But the period was wrong. Impossibly wrong. The signal repeated every 4 days. 4 days. If this was a planet, it was orbiting its star in the time it takes you to forget what you had for breakfast last Monday. For a planet to orbit that fast, it had to be close. Extraordinarily close. Closer than Mercury is to our Sun. And yet the wobble's amplitude suggested a mass similar to Jupiter. A Jupiter-sized planet, orbiting a Sun-like star, in 4 days. This was not supposed to exist. Every model of planetary formation said gas giants should form far from their stars, where temperatures are cold enough for volatile gases to accumulate. A hot Jupiter, as this type of world came to be called, challenged everything we thought we knew about how planetary systems are born. Mayer and Culo checked their data. They checked their instruments. They waited, watching 51 Pegasi through more orbits, more wobbles, more confirmations. The signal held. In October 1995, they announced their discovery. The first planet around a sun-like star. The first glimpse of what would prove to be an astonishing diversity of worlds. The reaction was electric. And skeptical. Some astronomers suspected another Van de Camp situation, another instrumental artifact masquerading as a discovery. But within days, an American team led by Jeffrey Marcy and Paul Butler confirmed the signal using their own instruments. 51 Pegasi b was real. The universe had planets we had never imagined. What happened next was a flood. Marcy and Butler had been searching for exoplanets for years, accumulating data without making announcements, waiting until they were absolutely certain. When 51 Pegasi b was confirmed, they went back through their archives. They found more hot Jupiters. They found planets on eccentric orbits, swooping close to their stars and then swinging far out, tracing elongated ellipses that looked nothing like the neat circles of our solar system. Within a few years, dozens of exoplanets had been discovered. Within a decade, hundreds. But something was still missing. The radial velocity method that found these worlds was biased toward large planets with short orbits. Those produced the biggest, fastest wobbles. Smaller planets, Earth-sized planets, were invisible to it. And planets on longer orbits, more like Earth's one-year journey around the Sun, required decades of patient observation to detect. We were finding the easy ones. The ones that screamed their presence. The quiet ones, the ones that might be like home, remained hidden. This is where Kepler changed everything. The idea was audacious. Build a space telescope, point it at a single patch of sky containing about 150,000 stars, and watch. Just watch. 4 years. Look for the tiny dimming, the fractional drop in brightness, that would occur when a planet passed in front of its star. The dimming would be small. An Earth-sized planet crossing a Sun-sized star would block about 1/100% of the star's light. Detecting that required extraordinary precision. But if you watched enough stars, for long enough, you would find something. Statistics guaranteed it. Kepler launched in March 2009. Within months, it had confirmed its first planets. But those early discoveries were not the point. The point was to find Earth-like planets in habitable zones. That required patience. A planet in a habitable zone around a Sun-like star would transit perhaps once a year. To confirm it, you needed to see multiple transits. Kepler was designed to stare at the same stars for at least 3.5 years. What those years revealed transformed our understanding of the galaxy. Planets are not rare. Planets are everywhere. Kepler found them around stars of all types. Hot stars, cool stars, large stars, small stars. It found systems with multiple planets, their orbital periods locked in elegant mathematical ratios. It found planets so close together that from the surface of one, another would loom larger in the sky than our moon. It found planets orbiting binary stars, circling two suns that circle each other, like Tatooine from Star Wars but real. And it found planets in habitable zones. Planets where temperatures might allow liquid water to exist on the surface. Planets that, at least in terms of size and location, resembled Earth. Not dozens. Thousands of candidates. The Kepler team estimated that there could be billions of Earth-sized planets in habitable zones throughout the Milky Way alone. Billions. The question, are there other worlds, had been answered so emphatically that it almost seemed ridiculous we ever asked it. But finding a planet is not the same as understanding it. A transit tells you a planet's size. The radial velocity method tells you its mass. Combine the two, and you get its density. Dense like rock, or fluffy like gas. From there, you can begin to guess at composition. But guessing is not knowing. To truly know what a planet is made of, what its atmosphere contains, whether it could possibly support life, you need to touch its light. This is what the James Webb Space Telescope was built to do. And this is where the story takes an unexpected turn. Because when Webb turned its golden mirror toward the atmospheres of distant worlds, it found something no one quite anticipated. Consider WASP 39b, a planet 800 light-years away. It is a hot Jupiter, not remotely Earth-like, bloated by the intense radiation of its nearby star. No one expected it to harbor life. But Webb studied its atmosphere anyway, because understanding alien atmospheres, any alien atmospheres, teaches us how to interpret what we see. The techniques developed on hot Jupiters will eventually be applied to smaller, cooler, potentially habitable worlds. Webb found carbon dioxide. That was expected. Carbon dioxide is common, stable, unremarkable. But Webb also found sulfur dioxide. That was not expected. Sulfur dioxide in WASP 39b's atmosphere is being created by photochemistry, by sunlight breaking apart other molecules and allowing new compounds to form. This was the first detection of photochemistry on an exoplanet. The atmosphere of that distant world is not static. It is active, evolving, driven by the energy of its star. Why does this matter? Because life is chemistry driven by energy. Photosynthesis is photochemistry harnessed by biology. Finding active chemistry in an exoplanet atmosphere is not finding life. But it is finding the kind of dynamic environment where life might emerge. And it proves that our instruments can detect these processes across interstellar distances. Then came K2-18b. This planet orbits a red dwarf star about 120 light-years away. It is larger than Earth, smaller than Neptune, a type of world we do not have in our solar system. It sits in its star's habitable zone. And when Webb analyzed its atmosphere, it found methane and carbon dioxide. It found hints of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by living organisms, by phytoplankton in the oceans. Let us be clear. This is not proof of life. The detection of dimethyl sulfide is tentative, not confirmed. Even if real, there may be non-biological explanations we have not yet imagined. The scientific community is appropriately cautious. But consider what has happened. We have gone from not knowing if other planets exist, to finding thousands of them, to detecting complex molecules in their atmospheres, to finding a possible biosignature on a world in a habitable zone. In 30 years, the pace is staggering. And it forces us to confront questions we barely knew how to ask a generation ago. If we do find convincing evidence of life on another world, what then? How will we confirm it? How will we understand it? How will we avoid fooling ourselves, as Van de Kamp fooled himself, as we are all capable of fooling ourselves? The history of exoplanet science is a story of humility learned and relearned. We thought we understood how planets form. Hot Jupiters proved us wrong. We thought we knew what planetary systems should look like. The wild diversity of actual systems shattered our expectations. We assumed our solar system was typical. It may be unusual. Perhaps even rare. And yet from all this uncertainty, patterns emerge. Most stars have planets. Small rocky worlds are common. Habitable zones exist around many different types of stars. The ingredients for life, water, organic molecules, energy, seem to be widespread throughout the cosmos. We are not looking for a needle in a haystack. We are looking for a particular needle in a haystack made entirely of needles. There is something almost vertiginous about this realization. When you look up at the night sky, every star you see likely has worlds circling it. Some of those worlds have surfaces you could stand on. Some have atmospheres you could, in principle, breathe. Some have oceans of liquid water, or skies streaked with clouds, or sunsets that paint the horizon in colors we have no names for. And we found them. Not through some gift of cosmic revelation, but through persistence, ingenuity, and the willingness to be wrong. Through decades of work by thousands of people, building on each other's successes and failures, checking and rechecking, doubting and confirming. The story of exoplanets is not just a story of discovery. It is a story of how we learn. How we push against the boundaries of what we know. How we refuse to accept ignorance as an answer. The next chapter of that story is being written now, with instruments that did not exist 10 years ago, using techniques that would have seemed like science fiction a generation past. And somewhere out there, on one of those billions of worlds, the question of whether we are alone may already have an answer. We just have not read it yet. But we are getting closer. Every day, we are getting closer, and here is what strikes you when you truly absorb this history. The people who made these discoveries possible did not know they would succeed. Peter van de Kamp did not set out to become a cautionary tale. He believed he had found something real. Mayer and Culo did not expect to append planetary science with a 4-day orbit. The Kepler team did not know if their instrument would survive launch, let alone revolutionize astronomy. Every step forward was a step into uncertainty. Every breakthrough emerged from the willingness to try something that might not work. Think about Bill Barucki, the NASA scientist who proposed the Kepler mission. He was rejected 4 times. 4 times, review panels told him it could not be done. The technology was not ready. The precision was not achievable. The cost was too high. He kept refining the proposal, kept advocating, kept believing. The 5th submission was approved. Kepler launched. And the universe opened up. This is the texture of discovery. Not the clean narratives of textbooks, but the messy, human, often frustrating reality of pushing against the limits of what is possible. Careers spent on single questions. Decades of incremental progress punctuated by sudden leaps. The ache of being wrong and the electric joy of being right. You are the beneficiary of all of it. The knowledge you carry, the understanding you have gained just by paying attention to this story, rests on the shoulders of people who spent their lives looking up and wondering. Some of their names are famous. Most are not. But each contributed something. Each moved us forward. And now we stand at a threshold. The instruments exist to detect biosignatures on potentially habitable worlds. The targets have been identified. The observations are being planned. Within the next decade, perhaps within the next few years, we may have data that changes everything. Or we may find that life is rarer than we hoped, more fragile, more dependent on conditions we do not yet understand. Either answer would be profound. The search for exoplanets taught us that planets are common. The next question is whether life is common too. And the tools to answer that question are in our hands right now, but exoplanets are only one of the 5 discoveries reshaping our understanding of the cosmos. There are others, equally revolutionary, equally strange. And they reveal not just what is out there, but what everything is made of. What the universe itself is doing. Where it came from and where it is going, the story continues. And the next chapter takes us to the darkest mystery of all. Imagine you are trying to weigh the universe. Not with a scale, obviously. With light. With mathematics. With decades of meticulous observation. You want to know how much stuff is out there, because that determines everything. The amount of matter in the universe dictates its shape, its fate, its future. Too much matter, and gravity eventually wins. The expansion that began with the Big Bang slows, stops, reverses. The universe collapses back on itself in a big crunch. Too little matter, and expansion continues forever, galaxies drifting apart until the cosmos becomes an endless, cold, empty void. In 1998, 2 teams of astronomers set out to measure which fate awaited us. They were competitors, racing toward the same answer, using the same method, driven by the same question. What they found instead broke physics. The method was elegant. Type Ia supernovae, those stellar explosions we discussed earlier, are standard candles. They all explode with roughly the same brightness. By measuring how bright a supernova appears, you calculate its distance. By measuring how much its light has been redshifted, stretched by the expansion of space during its journey to Earth, you calculate how fast it is receding. Do this for supernovae at different distances, and you can trace the history of cosmic expansion. You can see whether the universe was expanding faster in the past and is slowing down now, or whether the expansion rate has remained constant, or whether something else entirely is happening. Both teams expected to find deceleration. This was the obvious prediction. Gravity pulls. Matter attracts matter. The mutual gravitational pull of all the galaxies in the universe should be acting as a brake, gradually slowing the expansion. The only question was how much slowing. That would tell us how much matter the universe contains. Saul Perlmutter led the Supernova Cosmology Project, based at Lawrence Berkeley National Laboratory. Brian Schmidt led the High-Z Supernova Search Team, an international collaboration headquartered in Australia. They did not collaborate. They did not share data. They checked each other's work by trying to beat each other to the answer. Science at its most competitive. Science at its most human. The data came in slowly. Supernovae are rare. Finding them requires patience, luck, and telescope time that is always in short supply. Each detection triggered a frantic effort to measure the supernova's brightness and spectrum before it faded. Each measurement had to be corrected for dust absorption, for the supernova's position in its host galaxy, for a dozen subtle effects that could bias the results. Both teams worked for years, building their samples one explosion at a time. And then the graphs started to look wrong. The distant supernovae were too faint. Not by much, but consistently, persistently, stubbornly too faint. If the universe were decelerating, distant supernovae should appear brighter than the simple distance redshift relationship predicts, because the expansion was faster in the past, so those ancient photons did not have to travel quite as far as you might expect. Instead, the supernovae appeared dimmer, fainter, as if they were farther away than they should be. At first, both teams assumed they had made a mistake. They checked for dust. Dust absorbs light, makes things look dimmer. But the spectral signatures did not match dust absorption. They checked for evolution. Maybe supernovae in the early universe were intrinsically different, slightly fainter than modern ones. But the physics did not support significant evolution. They checked their instruments, their calibrations, their software. They checked everything. The data held. The supernovae were too faint because they were too far away. And the only way they could be too far away is if the expansion of the universe was not slowing down at all. It was speeding up. Think about what this means. Throw a ball into the air, and gravity slows it down. It rises, decelerates, stops, falls back. Now imagine throwing a ball into the air and watching it accelerate upward. Faster and faster, defying gravity, racing away from your hand with increasing speed. That is what the universe is doing. The galaxies are not just drifting apart. They are being pushed apart. And the pushing is getting stronger. Perlmutter's team published first, in early 1998. Schmidt's team followed within weeks, with independent data showing the same result. Two competing groups, using different telescopes, different software, different analysis methods, arriving at the same impossible conclusion. The universe is accelerating. Something is pushing it apart. That something needed a name. The astronomers called it dark energy, not because they understood what it was, but because they did not. Dark, as in hidden. Dark, as in unknown. A placeholder for ignorance wrapped in scientific terminology. Here is the terrifying part. Dark energy is not a minor component of reality. When you add up everything in the universe, all the matter, all the radiation, all the energy in every form we can detect, dark energy accounts for roughly 68% of the total. Ordinary matter, the atoms that make up stars and planets in your body, accounts for less than 5%. Dark matter, another mysterious substance we can detect only through its gravitational effects, makes up about 27%. We live in a universe dominated by things we cannot see, cannot touch, cannot explain. The discovery earned the 2011 Nobel Prize in Physics for Perlmutter, Schmidt, and Adam Rees, a key member of Schmidt's team. but a Nobel Prize is not an explanation. We still do not know what dark energy is. We have hypotheses. We have mathematical frameworks. We have names for our ignorance. But the fundamental nature of the force that dominates our universe remains a mystery. The simplest explanation is the cosmological constant, a term Einstein added to his equations of general relativity in 1917. Einstein introduced it to make the universe static, neither expanding nor contracting, because at the time everyone assumed the universe was eternal and unchanging. When Edwin Hubble discovered that galaxies were receding from us, proving that the universe was expanding, Einstein reportedly called the cosmological constant his greatest blunder. He removed it from his equations. But the cosmological constant never really went away. Mathematically, it represents an energy inherent to empty space itself. A vacuum energy. And quantum mechanics predicts that empty space should have energy, that virtual particles constantly pop in and out of existence, contributing to the vacuum's energy density. The problem is that when you calculate how much vacuum energy quantum mechanics predicts, you get a number that is roughly 10 to the power of 120 times larger than what we observe. That is not an error of 10% or even a factor of 10. That is a 1 followed by 120 zeros. It is the worst prediction in the history of physics. Something is canceling out almost all of that vacuum energy, leaving just enough to accelerate the expansion of the universe. We do not know what. We do not know why. We do not know how. This is called the cosmological constant problem, and it has haunted theoretical physics for decades. There are other possibilities. Maybe dark energy is not constant at all. Maybe it changes over time, a dynamic field that evolves as the universe ages. This hypothetical field is sometimes called quintessence, after the fifth element of ancient philosophy. Quintessence models can produce accelerating expansion, but they require new physics, new particles, new fields that we have never detected. They trade one mystery for another. Or maybe our understanding of gravity is incomplete. General relativity has been tested with extraordinary precision in our solar system and in the strong gravitational fields near neutron stars and black holes. But it has never been tested on cosmological scales with the same rigor. Maybe gravity behaves differently when you zoom out far enough. Maybe the acceleration we attribute to dark energy is actually a failure of our theory of gravity. This idea, called modified gravity, is controversial. It requires changing equations that have worked flawlessly for a century. But desperation breeds creativity, and the dark energy problem is desperate. The truth is, we do not know. And that uncertainty is not a weakness of science. It is science working exactly as it should. We observed something unexpected. We named it. We are now searching for its explanation. The answer may come from new telescopes mapping the distribution of galaxies across cosmic time. It may come from particle accelerators probing the quantum vacuum. It may come from a theoretical breakthrough that rewrites our understanding of space and time. Or it may remain a mystery for generations. But consider what the discovery reveals about the universe's fate. If dark energy continues to push, if the acceleration continues indefinitely, then the future is one of isolation. Galaxies outside our local group will eventually recede faster than light can travel. Not because they are moving through space faster than light, but because space itself is expanding faster than light can cross it. The galaxies will not disappear suddenly. They will fade, their light redshifting into invisibility, until nothing remains but the stars gravitationally bound to our own cosmic neighborhood. The rest of the universe will be forever beyond our reach. Forever beyond our knowledge. Trillions of years from now, astronomers in our galaxy, if any exist, will look up at a sky containing only local stars. They will have no evidence that other galaxies ever existed. The cosmic microwave background, the afterglow of the Big Bang, will have redshifted into nothingness. They will conclude, reasonably, that their galaxy is the entire universe. And they will be wrong. But they will have no way to know it. This is the future dark energy promises. Not a bang, not a crunch, but a slow, cold isolation. The universe expanding forever, its content spreading thinner and thinner, until heat death claims everything. Stars burn out. Black holes evaporate. Protons decay. And eventually, nothing remains but a faint haze of radiation, cooling toward absolute zero for eternity. Is this depressing? Perhaps. But there is another way to see it. We live in a remarkable window of cosmic time. Early enough that the universe is still full of structure, full of light, full of things happening. Late enough that we have evolved the intelligence to understand what we see. We exist in a brief moment when the universe is knowable, when galaxies are visible, when the story of cosmic evolution can still be read in the light that reaches us. In 100 billion years, that will no longer be true. But right now, today, you can look up at the night sky and see galaxies whose light has traveled millions of years to reach your eyes. You can know that those galaxies are racing away, pushed by a force that dominates reality yet eludes understanding. You can hold that mystery in your mind and marvel at it. The discovery of dark energy did something else, something perhaps more important than answering questions. It reminded us how much we do not know. In the late 20th century, there was a growing sense that physics was nearly complete. The Standard Model described particles and forces with stunning accuracy. General relativity explained gravity and the structure of spacetime. Cosmology had converged on a basic picture of the universe's history. Some physicists wondered if fundamental discoveries were over, if all that remained was filling in details. Dark energy shattered that complacency. Here was a phenomenon that made up most of the universe, yet had completely escaped our notice. Here was a force with no explanation in any existing theory. Here was proof that the cosmos still holds secrets we have not begun to imagine. And dark energy is not alone. We mentioned dark matter, the invisible substance that holds galaxies together. We know it exists because galaxies rotate faster than they should, as if unseen mass is adding its gravitational pull. We know it exists because light from distant galaxies bends around galaxy clusters more than visible matter can account for. We know it exists because the cosmic microwave background contains patterns that require dark matter to explain. But we do not know what dark matter is made of. It is not ordinary atoms. It does not interact with light. It passes through us, through Earth, through everything, without leaving a trace. Trillions of dark matter particles may be streaming through your body every second, and you would never notice. Experiments deep underground, shielded from cosmic rays, search for the rare collision between a dark matter particle and an ordinary atom. So far, they have found nothing conclusive. Dark matter remains dark. Together, dark energy and dark matter constitute 95% of the universe. 95%. We have built our entire understanding of physics from the 5% we can actually see and touch. The rest is mystery. This is not failure. This is invitation. Every great discovery in science began with a question we could not answer. Dark energy and dark matter are questions on a cosmic scale, questions that will drive research for decades, perhaps centuries. The answers, when they come, will reshape our understanding of reality itself. And somewhere in that reshaping, we may find connections we never expected. The quantum vacuum that may explain dark energy. The new particles that may constitute dark matter. The modifications to gravity that may unify our theories. These are not separate problems. They are facets of a single, deeper puzzle. The puzzle of what the universe actually is, beneath the surface we perceive. The discovery of accelerating expansion taught us humility. It taught us that the universe does not care about our expectations. It taught us that the most important discoveries are often the ones that prove us wrong. We thought we knew the universe's fate. We were wrong. And in being wrong, we found something far stranger and far more wonderful than the orderly cosmos we imagined. The darkness holds more than we knew. And we are only beginning to explore it, but let us return, for a moment, to that night in 1998. To the astronomers staring at their data, checking it for the dozenth time, feeling the ground shift beneath their feet. Adam Rees was 29 years old when he performed the analysis that confirmed the acceleration. He had written software to correct for the effects of dust and intrinsic brightness variations in supernovae. He ran the numbers. He got an impossible answer. He checked the code for bugs. He found none. He ran it again. Same answer. He later described the feeling as somewhere between amazement and horror. Horror, because the result contradicted everything they expected. Amazement, because if it was real, it was the discovery of a lifetime. He did not sleep much that year. Brian Schmidt remembers the moment he realized the data was not going to change. I was still expecting, every morning I woke up, that I would figure out what we had done wrong, he said. And then I finally realized we hadn't done anything wrong. These are not abstract moments in the history of science. These are human beings confronting the unknown, feeling the vertigo of discovery, wondering if they were about to make fools of themselves on the world stage. The universe does not reveal its secrets gently. It forces them upon you, ready or not, and you have to decide whether to trust what you see. Perlmutter, Schmidt, and Rees trusted what they saw. They published. They endured the skepticism, the demands for more data, the years of follow-up observations that confirmed the result over and over. And in 2011, they stood in Stockholm, receiving the Nobel Prize for showing that the universe is stranger than anyone imagined. That is what these top discoveries share. Not just the facts they revealed, but the courage they required. The willingness to say, this is what we found, even though it makes no sense. The discipline to check and recheck before speaking. And the persistence to keep searching, even when the answers only lead to deeper questions. We have explored 2 of our 5 discoveries in depth now. The multitude of worlds orbiting distant stars. The dark energy pushing the universe apart. But there are more. And the next one takes us not to the distant cosmos, but to our own cosmic backyard. To moons we dismissed as frozen wastelands. To oceans hidden beneath miles of ice. To the possibility that life, in some form, might exist far closer than we ever imagined. On a November evening in 2005, a spacecraft named Cassini was executing a routine flyby of one of Saturn's smaller moons. Enceladus was not the mission's priority. It was a bonus target, a frozen ball of ice barely 300 miles across, interesting mostly for its unusually bright surface. The main attractions were Saturn itself and Titan, the giant moon with its thick orange atmosphere and methane lakes. Enceladus was an afterthought. Then the cameras caught something impossible: plumes. Geysers. Jets of material erupting from fractures near the moon's south pole, shooting hundreds of miles into space, glittering in the sunlight like cosmic fountains. The images showed curtains of ice particles streaming outward, backlit by the distant sun, more dramatic than anything the mission planners had dared to imagine. The Cassini team scrambled. This was not in the script. This tiny, supposedly dead moon was actively venting material into space. Where was it coming from? What was driving it? They redesigned the mission on the fly, allocating precious fuel to additional Enceladus flybys, diving closer to the plumes, eventually flying directly through them. What Cassini tasted in those plumes would change our understanding of where life might exist in the universe: water, salt, silica nanoparticles that could only form in hot water interacting with rock, organic molecules, the carbon-based chemistry that forms the backbone of life as we know it, molecular hydrogen, a potential energy source for microbes. The plumes of Enceladus were not coming from some surface process. They were coming from an ocean. A global ocean of liquid water, hidden beneath the icy shell, kept warm by the gravitational kneading of Saturn's immense tidal forces. Picture it. Far from the sun, in the outer reaches of the solar system where temperatures plunge to hundreds of degrees below zero, there exists a world with more liquid water than many scientists expected to find anywhere beyond Earth. That ocean has a rocky seafloor. It has hydrothermal vents, places where heated water rich in minerals rises from below. On Earth, hydrothermal vents support entire ecosystems that thrive without sunlight, feeding on chemical energy alone. Tube worms, blind shrimp, ghostly white crabs, all living in perpetual darkness, all deriving energy from the chemistry of the vents. Could something similar exist beneath the ice of Enceladus? We do not know. But for the first time, we have a place to look. A place where the conditions that support life on Earth appear to exist on another world. And we can sample that ocean without even landing. The plumes deliver it to us, spraying ocean water into space where a spacecraft can fly through and analyze it. This is not science fiction. This is a mission that has already happened. Cassini operated at Saturn for 13 years before deliberately plunging into the planet's atmosphere in 2017, a planned end to prevent any possibility of contaminating the moons it had studied. But in those 13 years, it transformed Enceladus from a footnote into one of the most compelling targets in the search for life beyond Earth. And Enceladus is not alone. Europa, a moon of Jupiter, has been whispering its secrets for even longer. When the Voyager spacecraft flew past in 1979, they photographed a surface unlike anything else in the solar system. Smooth, young, crisscrossed by dark lines that looked like cracks in an eggshell. Almost no impact craters, which meant the surface was being constantly renewed, erased, resurfaced by some geological process. Something was happening on Europa. Something active. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, confirmed the suspicion. Europa's icy shell is floating on a liquid layer. The Moon's magnetic field fluctuates in a way that can only be explained by a global ocean of salt water beneath the ice. That ocean may contain twice as much water as all of Earth's oceans combined. It has been there for billions of years. Billions of years for chemistry to happen. Billions of years for complexity to emerge. We do not know if life exists on Europa or Enceladus. We do not even know if life can arise in such environments. The history of life on Earth is a single data point, and drawing universal conclusions from a single data point is dangerous. But what we do know is this: the ingredients are there. Liquid water. Energy. Chemistry. Time. The same ingredients that produced life here. And that changes everything. For most of the 20th century, the search for life beyond Earth focused on Mars. Mars has a thin atmosphere. Mars has polar ice caps. Mars has ancient riverbeds carved by water that flowed billions of years ago. Mars seemed like the obvious place to look. But Mars is cold and dry today. If life ever existed there, it may have died out eons ago. Finding it would mean finding fossils, traces, echoes of something long gone. The ocean worlds offer something different. They offer the possibility of life existing right now. Active, metabolizing, reproducing, evolving. Life that we could detect not by digging through ancient rocks, but by sampling the chemistry of an alien sea. Europa Clipper, a NASA mission launching in 2024, will conduct dozens of close flybys of Europa, studying its ice shell, its ocean, its potential for habitability. Future missions may land on the surface, drill through the ice, and release submarines into the dark waters below. We are not there yet. But we are planning. We are building. We are getting ready. The discovery of ocean worlds represents a fundamental shift in how we think about habitability. For decades, we assumed that liquid water required proximity to a star. Too close, and water boils away. Too far, and it freezes solid. The habitable zone, the so-called Goldilocks region, was defined by distance from a star. But Enceladus and Europa are nowhere near any habitable zone in the traditional sense. They are frozen wastelands on the surface. Yet beneath that surface, they harbor liquid oceans warmed by tidal heating, by the gravitational flexing caused by their giant planet hosts. This means habitable environments might be far more common than we imagined. Moons around gas giants in distant solar systems. Rogue planets drifting through interstellar space, carrying internal oceans heated by radioactive decay. Dark worlds, hidden worlds, worlds we would never detect by looking for Earth-like conditions around sun-like stars. The universe may be full of hidden oceans, and we have only just begun to realize it. But ocean worlds are not the only discovery that has reshaped our understanding of what is possible. We have also learned to perceive the universe in an entirely new way. We have learned to feel it. September 14, 2015. A Monday. At 5:51 in the morning, Eastern Time, a signal arrived at two detectors separated by nearly 2,000 miles. One in Livingston, Louisiana. One in Hanford, Washington. The signal was a chirp, a rising tone that swept upward in frequency over a fraction of a second before cutting off abruptly. It was not heard by human ears. It was seen on computer screens, a squiggle in the data that meant something extraordinary had happened. 1.3 billion years ago, in a galaxy we have no name for, two black holes spiraled together. Each was roughly 30 times the mass of our Sun. They had been orbiting each other for eons, drawing closer with each revolution, radiating energy in the form of gravitational waves. As they neared each other, the dance accelerated. The orbits tightened. The waves grew stronger. In the final moments, they were circling each other hundreds of times per second, approaching the speed of light, distorting spacetime so violently that the waves they emitted were stronger than any since the Big Bang. Then they merged. Two black holes became one, releasing an amount of energy equivalent to 3 solar masses converted entirely into gravitational radiation. For a brief instant, that collision was the most powerful event in the universe. More luminous, in gravitational waves, than all the stars in all the galaxies combined. The waves spread outward at the speed of light. They crossed 1.3 billion light-years of space. They passed through countless galaxies, countless stars, countless worlds, affecting nothing, noticed by no one. Until they reached Earth. Until they reached LIGO. The Laser Interferometer Gravitational Wave Observatory had been searching for exactly this signal for decades. The concept dated back to the 1960s, when physicist Joseph Weber claimed to have detected gravitational waves using aluminum cylinders. His results were never replicated. They were almost certainly wrong. But they sparked interest. They planted a seed. Rainer Weiss at MIT and Kip Thorne at Caltech took up the challenge. They designed a detector based on laser interferometry, splitting a beam of light and sending it down two perpendicular arms, then recombining it to look for tiny differences in the distance traveled. The idea was elegant. The engineering was nightmarish. Every source of noise had to be eliminated. Seismic vibrations, thermal fluctuations, quantum uncertainties in the laser itself. The project consumed careers. It nearly collapsed multiple times. Funding was uncertain. Critics called it impossible. Construction began in the 1990s. The original detectors were not sensitive enough. They were upgraded, improved, made more precise. By 2015, advanced LIGO had achieved sensitivity that would have seemed impossible a generation earlier. It could detect changes in distance smaller than 1/10,000th the diameter of a proton. And on that September morning, it worked. The chirp appeared in both detectors, 7 milliseconds apart, exactly the delay expected for a gravitational wave traveling at the speed of light between Louisiana and Washington. The waveform matched the predictions of general relativity with uncanny precision. There was no doubt. LIGO had detected gravitational waves. Einstein's century-old prediction was confirmed. Humanity had gained a new sense. The announcement came in February 2016, after months of careful verification. The scientific world erupted. This was not incremental progress. This was a threshold crossed. For all of human history, we had observed the universe through electromagnetic radiation, through light in all its forms. Now we could feel the vibrations of spacetime itself. We could hear the cosmos. In the years since, LIGO and its partner observatory Virgo have detected dozens of gravitational wave events. Merging black holes of various masses. Merging neutron stars, collisions so violent they forge gold and platinum in nuclear fire. Each detection teaches us something new. The population of black holes in the universe is different than we expected. Some are heavier than our models predicted. Some mergers happen in ways we do not fully understand. The gravitational wave sky is rich, complex, full of surprises. And then there is the image that started our journey. The shadow of a black hole. The Event Horizon Telescope is not a single telescope. It is a planet-sized array, a network of radio dishes scattered across 6 continents, linked together to function as one instrument. To image the event horizon of a black hole, you need resolution so fine that ordinary telescopes cannot achieve it. You need an aperture the size of Earth itself. The EHT creates a virtual telescope of that size by combining data from observatories in Hawaii, Arizona, Spain, Mexico, Chile, and the South Pole. The technique is called Very Long Baseline Interferometry, and it pushes the limits of what is technically possible. In April 2017, the entire array pointed at 2 targets. Sagittarius A*, the supermassive black hole at the center of our own galaxy. And M87*, the even larger black hole in the galaxy Messier 87, 55 million light-years away. For several nights, the telescopes recorded data. Petabytes of it. So much data that it could not be transmitted over the internet. It had to be physically shipped on hard drives to central processing facilities. Then came 2 years of analysis. Hundreds of researchers, working to combine the data, to calibrate it, to remove artifacts, to extract the image buried in the noise. The challenge was immense. The target was smaller than any object ever imaged at such distances. The data was incomplete, with gaps that had to be filled using sophisticated algorithms. Multiple teams worked independently, using different methods, to ensure the result was not biased by any single approach. On April 10, 2019, they revealed what they had found. A ring of light, bright on one side, dimmer on the other, surrounding a dark central shadow. The bright ring was superheated gas, spiraling inward at nearly the speed of light, radiating as it fell toward oblivion. The shadow was the event horizon, the boundary from which nothing, not even light, can escape. The asymmetry was caused by relativistic beaming, the Doppler effect amplified to extreme levels by the motion of the gas. There is a photograph from that day that captures something beyond the science. Katie Bauman, a young computer scientist who developed key algorithms for reconstructing the image, sitting in front of her laptop, hands over her mouth, eyes wide. The moment the image appeared on her screen. The moment decades of work by hundreds of people crystallized into a single picture that would be seen by billions. That photograph of a scientist seeing something impossible for the first time may be as powerful as the image itself. Shepard Doliman, the project director, described what it felt like. We have seen what we thought was unseeable. Think about those words. Unseeable. A black hole, by definition, emits no light. You cannot photograph it directly. What you can photograph is its shadow, the absence it creates, the silhouette against the inferno of matter falling into it. The EHT team did not just take a picture. They invented new ways of seeing. It looked almost exactly like the simulations. The predictions of general relativity, made over a century ago, matched the observation with stunning fidelity. A theory born in Einstein's imagination, expressed in mathematics, confirmed by an image of something 65 million trillion kilometers away. Think about what this represents. A human being, sitting at a desk in 1915, working out equations that described how mass warps space and time. Those equations predicted objects so extreme that even their creator doubted they could exist. A century later, other human beings built instruments capable of testing those predictions at the edge of the observable universe. And the equations held. This is the power of science. Not certainty, but testability. Not dogma, but evidence. The universe does not care what we believe. It simply is. And when we build instruments precise enough, and ask questions clearly enough, it answers. The discovery of ocean worlds taught us that habitability is not limited to Goldilocks zones. The detection of gravitational waves taught us that we can perceive spacetime itself. The imaging of a black hole taught us that our theories, however strange, can describe reality with extraordinary accuracy. These discoveries did not emerge in isolation. They are connected. The same Einstein who predicted gravitational waves also predicted black holes. The same techniques that analyze exoplanet atmospheres will someday analyze the plumes of Enceladus. The same spirit of inquiry that drove Cassini to fly through those unexpected geysers drove LIGO's builders through decades of technical challenges. We are living through a revolution in our understanding of the cosmos. Not a single breakthrough, but a cascade of them, each reinforcing and illuminating the others. The universe is vast, ancient, strange, and full of possibility. And we are only beginning to explore it. There is one more thing to consider before we reach the end of our journey. These 5 discoveries, extraordinary as they are, share a deeper meaning. They tell us something not just about the universe, but about ourselves. About what we are capable of. About what it means to be a species that asks questions and builds machines to answer them. That meaning is what awaits us in our final chapter. We began this journey with an image. A ring of fire surrounding a shadow, captured from 55 million light-years away. The first photograph of a black hole. The first glimpse of something so extreme that even its discoverer doubted it could exist. Now, after everything we have explored together, look at that image again. Not as a scientific achievement, though it is that. Not as a technological triumph, though it is that too. Look at it as a mirror. What you see in that image is not just a black hole in a distant galaxy. What you see is proof of what you are. What we are. A species that refuses to accept the darkness at face value. A species that builds planet-sized instruments to photograph the unphotographable, that listens for whispers in spacetime from collisions a billion years past, that tastes the spray of alien oceans erupting from frozen moons. A species that looked up at the stars and said, "We will understand you." That is the thread connecting all 5 discoveries we have witnessed. Not the facts themselves, stunning as they are. The act of discovering them. The audacity. The persistence. The sheer, improbable beauty of minds emerging from stardust and turning back to comprehend the stars. Think about what was required for any of this to happen. For the Event Horizon Telescope to capture that image, radio dishes on 6 continents had to observe the same target simultaneously, their data synchronized by atomic clocks accurate to billionths of a second. Weather had to cooperate at every site. Petabytes of information had to be physically shipped across oceans because no internet connection was fast enough. Hundreds of researchers had to develop new algorithms, new techniques, new ways of extracting signal from noise. And before any of that, generations of scientists had to develop the theory of relativity, build the first radio telescopes, invent the computers that would process the data, and establish the international collaborations that made coordination possible. One image. Decades of preparation. Centuries of accumulated knowledge. Millions of individual decisions, each one seemingly small, adding up to something unprecedented. This is how discovery works. Not as a lightning bolt from heaven, but as a slow accumulation. Layer upon layer of understanding, built by people who often did not live to see the fruits of their labor. The scientists who first detected radio waves from space in the 1930s never imagined we would use the technology to photograph black holes. The engineers who built the first lasers never dreamed they would be used to detect ripples in spacetime. But each contribution mattered. Each brick in the edifice was essential. You are part of this. Not as a passive observer, but as an inheritor. The knowledge you now carry, the understanding you have gained, exists because millions of human beings across thousands of years chose curiosity over comfort, chose questions over certainty, chose the hard work of figuring things out over the easy comfort of making things up. And now you carry that torch forward. Not necessarily as a scientist, though some of you may be, but as a conscious being who knows things about the universe that no human knew a generation ago. You know that planets orbit other stars. You know that dark energy pushes the cosmos apart. You know that oceans hide beneath the ice of distant moons. You know that gravitational waves ripple through spacetime. You know that black holes cast shadows. This knowledge changes you. It has to. You cannot truly absorb these discoveries and remain the same person you were before. Something shifts. Some boundary expands. Some sense of what is possible grows larger. Consider the scale of what we have learned. A century ago, we did not know other galaxies existed. We thought the Milky Way was the entire universe. Edwin Hubble changed that in the 1920s, showing that the fuzzy patches we called nebulae were actually distant island universes, each containing billions of stars. The cosmos expanded from one galaxy to billions in a single conceptual leap. 50 years ago, we did not know if planets existed around other stars. We suspected they might, but we had no evidence. Now we know of thousands, with billions more implied by the statistics. The cosmos expanded from one planetary system to countless. 20 years ago, we did not know that the expansion of the universe was accelerating. We assumed gravity was slowing it down. Now we know that dark energy dominates reality, pushing everything apart, shaping the ultimate fate of the cosmos. The cosmos became stranger, more dynamic, more full of mystery. 10 years ago, we had never detected a gravitational wave. We had never seen a black hole. We had never tasted the ocean of an alien moon. Now we have done all of these things. The cosmos has become not just knowable in theory, but actually known in practice. This is not a straight line of progress. There have been false starts, dead ends, discoveries that turned out to be mistakes. Science is messy. It contradicts itself. It argues with itself. It tears down what it built and builds again on the rubble. But through all of that, something real emerges. Something that works. Something that makes predictions you can test and technologies you can use and understanding you can trust. The 5 discoveries we have explored are not the end of anything. They are beginnings. Each one opens doors to questions we barely know how to ask. If exoplanets are common, is life common too? And if life is common, why have we not heard from anyone? The silence of the cosmos is deafening. Billions of potentially habitable worlds, and no signals, no visitors, no evidence of intelligence beyond our own. This is the Fermi paradox, and it haunts every conversation about our place in the universe. Maybe life is rare. Maybe intelligence is rare. Maybe civilizations destroy themselves before they can reach the stars. Or maybe we are looking in the wrong way, listening on the wrong frequencies, blind to forms of existence we cannot imagine. If dark energy is accelerating the expansion of the universe, what is it? The cosmological constant. A dynamic field. A failure of our theory of gravity. Or something else entirely, something that will require new physics, new mathematics, new ways of thinking we have not yet invented. The answer may reshape our understanding of space and time themselves. If ocean worlds harbor the conditions for life, do they harbor life itself? And if they do, what kind? Microbes clinging to hydrothermal vents. Something more complex. Something that would recognize us as alive, as we would recognize it. The missions to find out are being planned. The instruments are being built. Within our lifetimes, we may have answers. If gravitational waves can reveal the collisions of black holes, what else can they reveal? The moments after the Big Bang. The interiors of neutron stars. Phenomena we have not yet imagined. Every new sense opens new worlds. We are infants in the era of gravitational wave astronomy, learning to interpret sounds we have never heard before. And if we can photograph a black hole, what else can we photograph? The event horizon of Sagittarius A*, the black hole at the center of our own galaxy, has already been imaged. What about black holes in other states, black holes merging, the dynamic processes happening at the edge of the unseeable? The technology will improve. The images will sharpen. What we learn may challenge everything we think we know about gravity, space, and the nature of reality. These are not abstract questions for specialists in ivory towers. These are questions about what kind of universe you live in. About what is possible. About what your existence means in the context of 14 billion years of cosmic evolution. You are here, on a small rocky world, orbiting an ordinary star, in the suburbs of an ordinary galaxy, in a universe so vast that the light from its edge has been traveling since before the Earth existed. You are made of atoms forged in stars that died before your world was born. You are the cosmos contemplating itself. And you have the capacity to know this. To feel it. To let it change you, that is the real discovery. Not the black holes or the exoplanets or the gravitational waves. The discovery is that you can discover. That the universe is comprehensible. That a mind can emerge from matter and turn back to understand the matter from which it emerged. This is not obvious. This is not guaranteed. This is perhaps the strangest thing of all. Why should reality be understandable? Why should mathematics describe the motions of galaxies? Why should human intuition, evolved to navigate the African savanna, prove capable of grasping the curvature of spacetime? These questions have no easy answers. Some would say it is evidence of design. Others would say it is anthropic selection, that we exist in a universe where comprehension is possible because only such a universe could produce comprehenders. Still others would say we should simply be grateful and get on with the work. Whatever you believe, the fact remains. We can understand. We do understand. And that understanding connects you to every scientist who ever stayed up late puzzling over data, every engineer who ever pushed the limits of what machines could do, every dreamer who ever looked up at the night sky and wondered. So where do we go from here? The James Webb Space Telescope is studying the atmospheres of exoplanets right now, searching for signs of life. LIGO is being upgraded to detect even fainter gravitational waves. Europa Clipper is preparing to explore an ocean world. New telescopes, new missions, new questions are being planned, funded, built. The enterprise continues. But it does not continue automatically. It continues because people choose to continue it. Because societies decide that understanding the universe is worth the cost. Because individuals choose to spend their lives on questions that may not be answered in their lifetimes. Because you, sitting wherever you are, reading or listening to these words, care enough to pay attention. Your attention matters. Your curiosity matters. The fact that you stayed with this story, through black holes and exoplanets and dark energy and ocean moons and gravitational waves, means something. It means the spark is there. The same spark that drove Galileo to point his telescope at Jupiter. The same spark that drove Einstein to imagine riding a beam of light. The same spark that will drive whatever discoveries come next. You do not have to be a scientist to carry that spark. You just have to stay curious. Keep asking questions. Keep demanding evidence. Keep looking up. The universe does not owe us comprehensibility. It does not owe us wonder. It does not owe us anything. But it offers these gifts anyway, to anyone willing to receive them. And receiving them is a choice. A choice to engage rather than ignore. A choice to marvel rather than scroll past. A choice to let the bigness of reality expand the smallness of daily concerns. There is a photograph of Earth taken by Voyager 1 in 1990, from a distance of 6 billion kilometers. In that image, Earth is a pale blue dot, a fraction of a pixel, suspended in a beam of sunlight. Carl Sagan wrote about that image with words that still resonate. Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam. That mote of dust produced minds capable of photographing black holes. That mote of dust sent spacecraft to taste the oceans of distant moons. That mote of dust learned to hear the collisions of objects so dense that light cannot escape them. We are small. Unimaginably small. A single planet in a single solar system in a single galaxy in a universe containing 2 trillion galaxies. And yet we are large. Large enough to contain the knowledge of all of this. Large enough to feel wonder. Large enough to ask why. The 5 discoveries we have explored are milestones on a journey that has no end. There will always be more to learn. Always another horizon. Always another question that seems impossible until someone figures out how to answer it. And somewhere out there, right now, someone is working on the next discovery. Someone is analyzing data that will change everything. Someone is having an idea that will seem obvious in hindsight but is utterly revolutionary right now. The story continues. It has to. Because that is what we do. We look up. We wonder. We reach, and sometimes, against all odds, we find something that makes the reaching worthwhile. So let me leave you with this: what does it feel like to know what you now know? To carry inside you the image of a black hole, the sound of spacetime rippling, the taste of an alien ocean, the light of 1,000 distant worlds, the weight of a universe accelerating into darkness. Does it make you feel small? Does it make you feel large? Does it make you feel alone, or connected, or both at once? What question, of all the questions we have raised, burns brightest in your mind? What would you want to know, if you could know anything? What discovery would change you most deeply? And here is the question that matters most: what will you do with this? Not in some grand, save the world sense, but in the small, daily sense of how you move through life. Will you stay curious? Will you keep asking? Will you let the universe in, even when it is easier to look away? These questions have no right answers. They are invitations. Invitations to continue the conversation, with yourself, with others, with the cosmos that made you and that you are slowly, painstakingly, beautifully learning to understand. If these ideas resonate with you, if this kind of exploration feels like something you want more of, then you are not alone. There are others who feel the same pull. Others who want to keep looking up, keep asking questions, keep pushing against the boundaries of what we know. Find them. Talk to them. Share what you have learned and listen to what they have discovered. The greatest journeys are not taken alone. The universe is vast and old and strange. But it is also here, all around you, waiting to be noticed. The same atoms that form black holes form your bones. The same forces that shape galaxies shape your heartbeat. You are not separate from the cosmos. You are part of it. The part that wonders. And that wondering, that reaching, that refusal to stop asking why, is perhaps the most beautiful thing the universe has ever produced. So keep wondering, keep reaching, the stars are waiting.